Hello, good morning. Oh, sorry, good evening.
Good evening, sir.
Good evening. Today we will discuss the organic chemistry and hydrocarbon. Organic chemistry is the chemistry of carbon compounds, and the reason for the compounds of carbon, the single element, is studied as organic chemistry. As a separate branch is enormous number of compounds, that is more than 10 million carbon compounds are known today. And the total number of compounds produced by all other elements are less than the compounds of carbon. That is why it is studied as a separate branch, organic chemistry. Anyway, I am not going to the details. I am going to the questions directly. That is, the first question is the number of primary, secondary, and tertiary carbon atoms in 2,3-dimethyl pentane. That is, the parent organic compounds are hydrocarbons. And the hydrocarbons are the compounds containing only two elements, carbon and hydrogen. And these hydrocarbons, they can be broadly classified into open chain hydrocarbons and closed chain hydrocarbon. The open chain hydrocarbon itself is further classified into saturated and unsaturated. And the saturated means there is no carbon-carbon double bond or triple bond. There is only carbon-carbon single bond. And that is saturated open chain hydrocarbons. And they are known as alkanes, and their generic formula is CnH2n plus 2. That is, alkanes are having generic formula CnH2n plus 2, and they are open chain hydrocarbon, and there is no carbon-carbon double bond or triple bond. And if there is double bond, it is called alkenes. Their generic formula is CnH2n. If there is triple bond, it is alkynes, and its generic formula is CnH2n minus 2. And while naming, you have to select the longest carbon chain. And in the case of alkanes, the suffix is ane, and for alkene it is ene, and for alkynes it is yne. And that about in the case of, that is the nomenclature of the hydrocarbons, alkanes, alkenes, and alkanes. And we know that there is 2,3-dimethyl pentane means there are 5 carbon atoms in a straight chain. Pentane, there are 5 carbon atoms in a straight chain. And 2,3-dimethyl means that is 2 methyl groups are on second and third carbon atom. That is 2,3-dimethyl pentane. And we have to substitute the other valency by hydrogen. So for CH3, 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 CH2, CH3, carbon is always tetravalent in its compound, and therefore this is the 2,3-dimethyl pentane. And the primary carbon atom is a carbon atom in which, that is, it is attached to only one another carbon atom, or if it is not attached to any other carbon atom. Methane, it is a primary carbon atom, CH4. Ethane, CH3, CH3. There are 2 primary carbon atoms. And secondary carbon atom is a carbon atom in which it is bonded to 2 other carbon atoms. Propane, CH3, CH2, CH3. And CH3, it is primary, CH2, it is secondary, and CH3, it is primary because the CH2 group, it is bonded to 2 other carbon atoms. Similarly, if a carbon atom is bonded to 3 other carbon atoms, it is tertiary, and if it is bonded to 4 other carbon atoms, it is quaternary, and that is primary, secondary, tertiary, and quaternary carbon atom. Here, this carbon atom is bonded to only one another carbon atom, it is primary. This is also bonded to another carbon atom. This is also a primary. This is also a primary. There are 4 primary carbon atoms, and this is a tertiary carbon atom because it is bonded to 3 other carbon atoms. This is also a tertiary carbon atom because it is bonded to 3 other carbon atoms. This is a secondary carbon atom because it is bonded to 2 other carbon atoms. And therefore, there are 4 primary carbon atoms and 1 secondary carbon atom and 2 tertiary carbon atoms in 2,3-dimethyl pentane. And therefore, the answer is C. The state of hybridization of 4 carbon atoms from left to right in the molecule CH3, CH double bond, CHCN, CH3, CH double bond, CHCN. And that is, if a carbon atom is bonded to 4 other, that is single bonds are there, that means it is sp3 hybridized. sp3 means there are 4 hybrid orbital, and hybrid orbital will form only sigma bond. And here the single bonds are sigma bond, and the double bond is a combination of 1 sigma and 1 pi bond. Triple bond is a combination of 1 sigma and 2 pi bond. And here we can see that this carbon atom, it is bonded to 3 hydrogen atom, 3 sigma bonds, and it is bonded to carbon atom, and therefore the 4 are sigma bond, and therefore this carbon atom is sp3 hybridized. Here this carbon atom contains 1 carbon-carbon single bond and 1 carbon-hydrogen single bond, and there is a carbon-carbon double bond. That means 3 sigma bond and 1 pi bond. Therefore, it is sp2 hybridized. Similarly, this carbon atom is also sp2 hybridized, and Cn means carbon-nitrogen triple bond, and therefore there are 2 sigma bond and 2 pi bond. It is sp hybridized. That is, in that compound, the first carbon atom is sp3, the second and third carbon atoms are sp2, and the fourth carbon atom it is sp hybridized from left to right, and therefore the answer is sp3, sp2, sp2, sp. That means it is choice A. Third question is the total number of sigma bonds and pi bonds in prop 2 nitrile. Prop 2 nitrile means it is nothing but prop 2 nitrile means CH3, CH double bond, that is nitriles are cyanides, and prop means there are 3 carbon atoms, and therefore it is prop 2 nitrile means this is first carbon atom, this is second carbon atom, and there is a double bond between the second and third carbon atom, and therefore it is CH2, CH, C triple bond N. This is, that is CH2, CH, CH2 double bond CH, single bond Cn, and that is the prop 2 nitrile. And sigma bonds are single bond, and double bond is a combination of 1 sigma and 1 pi bond, and therefore there are how many sigma bonds and how many pi bond? 1, 2, 3, 4, 5, 6. 6 sigma bonds, and there are 1 and plus 2, 3 pi bond. In prop 2 nitrile, there are 6 sigma bonds and 3 pi bond. Therefore, the answer is B, 6 and 3. Identify the heterocyclic compound among the following. That is, we have already mentioned that there is open chain hydrocarbons and closed chain hydrocarbon. A closed chain hydrocarbon will have a ring structure, and that is the closed chain hydrocarbon. It is having a ring structure, therefore it is cyclic in nature. And that is here, what is asked is identify the heterocyclic compound. The cyclic compounds can be broadly classified into homocyclic if there is only carbon atom in the cyclic process, and if an atom other than carbon atom in the cyclic process, for example, in pyridine it is nitrogen, in furan or pyrrole it is oxygen. Likewise, and they are known as heterocyclic compounds. And here, aniline, it is nothing but aminobenzene. And benzene, there is all the 6 carbon atoms are in the cyclic structure. It is not heterocyclic. Naphthalene, it is a combination of 2 benzene ring, and therefore there is only carbon atom in the cyclic structure. It is homocyclic. And similarly, that is triopolin and that is cyclohexanone. They are also having only carbon atom in the cyclic structure, whereas pyridine contain nitrogen as the heteroatom, and therefore pyridine is an example for a heterocyclic compound. Answer is D. The correct decreasing order of priority of functional groups in the IUPAC system of nomenclature. In IUPAC system of nomenclature, I have mentioned that for alkane, the suffix is ane, for alkene it is ene, and for alkyne it is yne. But if there is a functional group, for example, OH group, it is alcohol, CH3OH, it is methane, or CH4 is methane, and if the E of the alkane is replaced by oil, methanol, that is CH3OH. That is, in the case of alcohol, E of the alkane is replaced by oil. Similarly, in aldehyde, that is CHO group is aldehyde group, it is E of the alkane is replaced by Al, alkanal. And if CO is the functional group, it is ketone, and therefore alkanone is replaced by ONE. And likewise, the functional group is having different suffix. And if there is more than one functional group in a compound, there is an order of preference. And you have to select the preferred functional group, and the other functional groups are expressed as the substituents. For example, in the case of carboxylic acid, COOH, OIC acid is the that is in the case of carboxylic acid, the functional group is named as OIC acid. Therefore, it is HCOOH. It is methanoic acid. There is only one carbon atom. Alkane is methane. E is replaced by OIC acid, methanoic acid. CH3COOH. There are 2 carbon atoms, ethane, and therefore it is known as ethanoic acid. And that is in the case of carboxylic acid. And if propanoic acid, CH3, CH2, COH, and if there is a OH group also in that compound, and then the preference is for COH group, and therefore it is known as propanoic acid, and the OH group is taken as the that is, it is substituent, and therefore you will get hydroxy. That is, if it is attached to the second carbon atom, it is 2-hydroxypropanoic acid. If it is attached to the third carbon atom, it is 3-hydroxypropanoic acid. And similarly, if there is more than one, that is functional group, the name is derived from that major functional group. There is an order of preference. And here it is asked is the correct decreasing order of priority of functional group in the IUPAC system of nomenclature. It is choice A, carboxylic acid, greater than, that is prior than the sulfonic acid, which is more preferred than cyanide or nitrile, which is more preferred than the aldehyde, which is more preferred than the hydroxyl group. And that is the choice is A. The correct IUPAC name of the following compound is, and we can see that the formula of, that is, the compounds can be written in various ways. That is, we can write, for example, in the case of propane, that is, it is CS3, CS2, CS3. This is a detailed structural formula of propane. All the bonds are that is given, and CS3, CS2, CS3, it is propane. And the condensed structural formula is CS3, CS2, CS3. But this can be expressed as bond line formula, and in bond line formula you are not expressing the carbon atom or the hydrogen atom. It is propane. That means this is terminal carbon atom and it is bonded to another carbon atom. Therefore, the other three valencies are saturated by hydrogen. It is CS3, this is CS2, and this is CS3. And this is in the case of propane. If it is 2-chloropropane, CS3, CHCl, CS3, you have to show what is the substituent chlorine. This is 2-chloropropane. And similarly, if it is carboxylic acid, COOH, that is, for example, that is CS3COOH. This is CS3COOH. This is acetic acid or ethanoic acid, and that is known as the bond line formula. And this bond line formula, it is given, and you have to identify the compound. It is nothing but that is COH, and therefore it is CS3. CS3. This is CS2. CS2. This is also CS2. This is COOH, and here it is chlorine is there. Therefore CHCl, CS2, COOH. This is the structural formula of that compound, and therefore COH group is having the preference, and therefore it is, that is 1, 2, 3, 4 butanoic acid, and there is a chlorine atom on the first, second, and third carbon atom. Therefore it is 3-chloro-butanoic acid. The compound is having the nomenclature 3-chloro-butanoic acid. Choice is B. Which among the following is neopentyl group? That is in common naming. There is IUPAC nomenclature as well as common naming. In common naming, that is, if you consider there is a, that is, if it is CS3, CHCS3, CS3, the IUPAC nomenclature is 2-methyl propane. It is 2-methyl propane. But in common naming, there are 4 carbon atoms. Therefore, it is nothing but a derivative of butane. And therefore, it is known as, that is, it is N but 1 methyl group is there. This is the N carbon atom. And before that, there is a methyl group. In such cases, it is named as iso. Therefore, it is isobutane. 2-methyl propane is known as isobutane. And if there are, that is, 2-methyl group on the N but 1 carbon atom, it is known as neo. And therefore it is, there are total 5. Actually, its IUPAC nomenclature is 2,2-dimethyl propane. But if there are 2-methyl group on N but carbon atom, it is neo. It is neo, and total there are 5 carbon atoms. Therefore, it is neopentane. That is, if there is a methyl group on the N but 1 carbon atom, it is iso. If there are 2 methyl group on the N but 1 carbon atom, it is known as neo. And that is in the case of common naming. Here what is asked is, which among the following is a neopentyl group? A neopentyl group means there should be 2 methyl group on the N but 1 carbon atom. In choice D, CS3 tri-C, CS3 tri-C, and CS2. It is that is neopentyl group. If an hydrogen atom is replaced from, that is, the alkane, it is known as alkyl group, and therefore it is neopentyl group. This is neopentyl group. Therefore, the answer is D. Identify the alkene that does not exhibit geometrical isomerism among the following. That is, the isomerism is the phenomenon of existence of different compounds with same molecular formula. We have already mentioned the isomerism in the case of coordination complexes. And in organic chemistry, there is isomerism. We have mentioned that actually the carbon compounds are studied as a separate branch because of the number of carbon compounds. More than 10 million carbon compounds are known today, and more carbon compounds are day by day detected. And the reason is That is, there is one phenomena called isomerism, the existence of different compound with same molecular formula. In the case of inorganic chemistry, there is no such. For example, in the case of sodium chloride, NaCl, there is only one compound, NaCl. H2SO4, sulfuric acid, there is only one compound with molecular formula H2SO4. And in the case of, that is, sodium hydroxide, it is NaOH. And similarly, there is only one compound with one molecular formula. But in the case of organic chemistry, there is more than one compound with the same molecular formula. For example, in the case of C4H10O, a compound with molecular formula C4H10O, C4H10O. And there is 7 compounds with same molecular formula C4H10O. One is CS3, CS2, CS2, CS2OH. This is butane 1-ol. This is butane 1-ol. And if the OH group is on the second carbon atom, CS3, CS2, CHOH, CS3. This is butane 2-ol. And if the carbon atoms are, 3 carbon atoms are on straight chain, CS3, CS2, CS3, CH, CS3, CS2OH. This is 2-methyl propane 1-ol or isobutyl alcohol. And if there is OH group is on this second carbon atom, CS3, CHOH, COH, CS3, CS3. This is 2-methyl propane 2-ol or it is tertiary butyl alcohol. These are all alcohol, and here the 1 butanol and 2 butanol, example for position isomers, because the OH group is on the first carbon atom, here it is on the second carbon atom. And here the carbon chain, there is difference. That is, here all the 4 carbon atoms are on a straight chain, but here 3 carbon atoms are on straight chain, 1 is branched chain, and therefore it is a chain isomer. Butane 1-ol and 2-methyl propane 1-ol are chain isomers. And similarly, butane 2-ol and 2-methyl propane 2-ol are chain isomers. And therefore, there are 4 alcohols with same molecular formula. And if you consider the alcohols and ethers, for example, CS3, CS2, OCS2, CS3. This is dimethyl ether or ethoxyethane. It is an ether. And if it is CS3, OCS2, CS2, CS3, this is methoxypropane, 1-methoxypropane. That is another ether, and the positions of the functional group is different. They are called metamers. And if there is CS3O, CH, CS3, CS3, it is 2-methoxypropane. And that is, it is also a metamer. Therefore, there are 3 ethers with molecular formula C4H10O and 4 alcohols with molecular formula C4H10O. There are altogether 7 organic compounds with molecular formula C4H10O. They are called isomers. And here, these are structural isomers because their structural formula is different and they are having same molecular formula. But they can also exhibit another type of isomerism, geometrical isomerism and optical isomerism. Geometrical isomerism arises only when there is carbon-carbon double bond, and a compound with molecular formula CAB double bond CAB, where A is not equal to B, can exhibit geometrical or cis-trans isomerism. That is, CAB double bond CAB. This is a cis isomer because the like atoms or groups are on the same side of the carbon-carbon double bond. And if they are on the opposite side, then it is called the trans isomer. And this is the trans isomer. And this cis-trans isomerism is called geometrical isomerism. And the geometrical isomerism arises due to the that is restricted rotation of the carbon-carbon double bond. That is, a carbon-carbon single bond is a sigma bond and free rotation is possible, but a carbon-carbon double bond is, that is, there is restriction about the free rotation and therefore it cannot be rotated and therefore it exhibits the geometrical isomerism, the cis isomer and the trans isomer. And that about the geometrical isomerism. There is another type of stereoisomerism is optical isomerism. The optical isomerism means they are having the same molecular formula, same structural formula, and their physical properties and chemical properties are same. Only their orientation of atoms or group of atoms in space is different, and thereby their action is when a plane polarized light is passed through this compound, it will rotate the plane of the plane polarized light either to the right hand side, that is known as dextrorotatory, and if it is, that is rotating the plane polarized light to the left hand side, it is known as levorotatory, and that is known as optical isomerism. And for exhibiting optical isomerism, organic compound must contain, that is, asymmetric carbon atom. What is asymmetric carbon atom? A carbon atom in which the 4 valencies are satisfied by 4 different atoms or group of atoms, and that is known as asymmetric carbon atom. If a compound containing asymmetric carbon atom, then only it can exhibit optical isomerism. And these are the various type of isomerism. That is, the isomerism is the phenomenon of existence of different compound with same molecular formula. They can be broadly classified into structural isomerism and stereo or space isomerism. Structural isomerism is further classified into chain or nuclear isomerism, which arises due to a difference in the carbon chain. And then there is position isomerism. It arises due to difference in the position of the same functional group. And another is the functional isomerism. It arises due to a difference in the functional group. For example, alcohols and ethers. Alcohol, the functional group is OH, and ether, the functional group is, that is, the functional group is ethereal oxygen, and therefore that is the functional group is different, but both are having the same molecular formula, and that about the functional isomerism. Then there is the metamerism. It is a particular type of positional isomerism exhibited by ethers and esters, and that about the structural isomerism. Then there is stereoisomerism, geometrical and optical isomerism. Geometrical isomerism arises due to the restricted rotation of the carbon-carbon double bond, and the compounds with molecular formula CAB double bond CAB, where A is not equal to B, can exhibit geometrical or cis-trans isomerism. And optical isomerism is exhibited by compounds containing asymmetric carbon atom. Asymmetric carbon atom is a carbon atom in which the 4 valencies are satisfied by 4 different atoms or group of atoms. Here what is asked is, that is, identify the alkene that does not exhibit geometrical isomerism among the following. For exhibiting geometrical isomerism, the formula must be CAB double bond CAB, where A is not equal to B. And here the choices are 2-chlorobutene. 2-chlorobutene means CS3, CH double bond CH, CS3 is 2-butene, and 2-chlorobutene is this compound, and here A is not equal to B, therefore it can exhibit of the geometrical isomerism CAB, where the CAB double bond CAB, where A is not equal to B. 2,3-dibromobutene, 2,3-dibromo-2-butene. That is, here also it can exhibit the geometrical isomerism because it is CAB double bond CAB where A is not equal to B. 2,3-dimethyl butene. 2,3-dimethyl butene means the two methyl group are the substituent. Here A is equal to B, and therefore 2,3-dimethyl butene cannot exhibit the geometrical isomerism. Therefore, the answer is C. The compound CS3, CS2, CS2, C triple bond CH and CS3, C triple bond C, CS2, CS3R. There is the functional group is triple bond, and in the first compound it is attached to the first carbon atom, and in the second compound it is bonded to the second carbon atom. Therefore, they are position isomers. The name of the compound is, here it is 5 carbon atom. It is, therefore it is pent 1 ion and pent 2 ion. They are position isomers. The choice is A. The number of structural isomers possible for C5S10 and C5S10, it is having a large number of 10 isomers, because in the case of C5S10, it is an that is generic formula for an alkene. C5S10 is a generic formula for alkene, CnH2n, and therefore it can be that is pent-1-ene, and it can be pent-2-ene, it can be 3-methyl but-1-ene, it can be 2-methyl but-2-ene, it can be 2-methyl but-1-ene, and it can be cyclopentane. That is cycloalkanes and alkenes are, that is isomers, or it is methyl cyclobutane, or ethyl cyclopropane, or 1,2-dimethyl cyclopropane, or it can be 1,1-dimethyl cyclopropane. Altogether, there are 10 isomers with molecular formula C5S10. Therefore, the answer is E. In which among the following effects the sigma electrons of carbon-hydrogen bond of the alkyl group enter into the partial conjugation with the attached unsaturated system or with the unshaded p orbital? It is nothing but the hyperconjugation effect, the no bond resonance or hyperconjugation effect. And here the inductive effect is a permanent electron displacement occurring in organic molecule through the carbon-carbon sigma bond or single bond, and that is inductive effect. And there is minus I effect, and if a group is having that is capability of that is pulling the electron, if the electron is pulled towards itself, that atom or molecule is having minus I effect. If it is having a property of that is pushing the electron, then it is the plus I effect. Therefore, there are plus I effect and minus I effect, as well as the electromeric effect is a temporary electron displacement occurring in compound containing carbon-carbon double bond, and it is occurring only at the time of the reaction. After the reaction, it will disappear. Therefore, electromeric effect will always favor a reaction. And hyperconjugation or no bond resonance, it is that is the shifting of carbon-hydrogen bonded pair to a carbon-carbon single bond to give a carbon-carbon double bond. That is known as no bond resonance or hyperconjugation. Identify the incorrect statement among the following. Polarization of sigma bond caused by the polarization of adjacent sigma bond is referred to an inductive effect. It is true. The difference in energy between the actual structure and the lowest energy resonance structure is called the resonance energy. It is also true. Resonance effect operates in molecule containing conjugated, that is pi bond. It is also true. Conjugated pi bond means the sigma and pi bond are alternate, and that is in benzene. There is resonance because there is alternate single and double bond. Then electromeric effect takes place in presence of an attacking reagent only. That is also true. That is electromeric effect operate only at the time of the reaction. and hyperconjugation is a temporary effect. It is wrong. Hyperconjugation is a permanent effect. Therefore, answer is E. Minus A effect of the following groups increases in the order. The minus A effect is the electron pulling effect. Electron തന്നിലേക്ക് വലിച്ചടിപ്പിക്കാനുള്ള കഴിവിനെയാണ് minus A effect എന്ന് പറയുന്നത്. And the minus A effect increases as the electronegativity of the group also increases. Here the minus A effect is in the order, that is ഏറ്റവും highest minus A effect is for nitro group, then for cyano group, then for carboxylic acid, then for chlorine. That is chlorine less than, CO is less than, CN less than NO2. That is choice is D. And that about the inductive effect. Then question number 14. The major product obtained when a mixture of butene and hydrogen is passed over heated Lindlar catalyst. What do you mean by Lindlar catalyst? Lindlar catalyst is hydrogen and palladium in presence of barium sulfate, or hydrogen and palladium in presence of barium carbonate, etc. Isoquinoline, etc. That is, in presence of the barium sulfate, the catalytic activity of the palladium is restricted, and therefore the reduction process, hydrogen is a very good reducing agent. And in the case of alkyne, alkynes are compound containing carbon-carbon triple bond, and when it is added with hydrogen, initially the one double pi bond is broken and you will get a hydrogen is added, you will get alkene. Again 1 mole of hydrogen is added and you will get a alkane. That is 2 moles of hydrogen is added to the carbon-carbon triple bond. But if you are using a Lindlar catalyst, the catalytic activity is restricted. Thereby only 1 mole of hydrogen atom is added to the carbon-carbon triple bond, and thereby you will get a alkene. And this reduction, it is carried out by Lindlar catalyst, and you will get, that is, you can carry out the addition of hydrogen by another method also. But if you are using Lindlar catalyst, you will get cis-butene. That is, in the case of butene, it is CH3CH double bond CH3, and that is 2 methyl groups are on the same side of the carbon-carbon double bond, and 2 hydrogen atoms are on the opposite side. That is, you will get cis-2-butane. But if you are using sodium and liquid ammonia, there also reduction takes place, and the addition product will be trans-2-butane, and that is, it is known as Birch reduction. And therefore, if you are using a Lindlar catalyst, the answer is cis-butene. And if you are using, instead of Lindlar catalyst, sodium and liquid ammonia, you will get trans-butene. Therefore, here the answer is B. Reaction of HBr with propene in presence of peroxide is an example of addition of HBr to an alkene. It follows Markovnikov addition. That is, it is an electrophilic addition mechanism. Carbon-carbon double bond, it is 5 electrons are there, therefore it is electron rich, and therefore when you treat it with HBr, H plus will attack the carbon-carbon double bond. That is, it is electrophilic addition reaction. What do you mean by that? Is electrophile and nucleophile. That is, electrophiles are electron deficient species which is having an affinity towards the electron rich center. For example, H plus, Cl plus, these are all electrophiles. Cations are electrophiles, or electron deficient species are electrophile, electron loving group. But if it is having, that is, electron rich, for example ammonia, there is a lone pair on the nitrogen atom, and therefore it is a nucleophile. It is having an affinity towards the positively charged carbon center, and that is, positive charge on atom is in the nucleus. Therefore they are known as nucleophiles. Cl plus is a nucleophile. H plus, it is an Cl plus is an electrophile. Cl minus is a nucleophile. Similarly, that is OH minus. It is a nucleophile, hydroxyl ion, or RO minus, alkoxide ion. They are all nucleophiles. Cations are electrophiles and anions are nucleophiles. And the addition of HBr to the alkene, it follows the electrophilic addition, because H plus, HBr dissociate to give H plus and Br minus, and H plus will be added to the carbon-carbon double bond. The pi bond is shifted to one of the carbon atom, gaining it a negative charge, and H plus will be added to that carbon atom, and the other carbon atom will have a positive charge, and there Br minus will be added, and you will get the product. But if an unsymmetrical alkene is taken, the addition of HBr to the unsymmetrical alkene, it follows Markovnikov rule. The negative part of the addendum goes to the carbon atom containing least number of hydrogen atoms. That is, propene is an unsymmetrical alkene. CS3, CS double bond, CS2. What is symmetrical and unsymmetrical? Butene. It is a symmetrical alkene because the group on the carbon-carbon double bond is same. That is CH3CH double bond CH3, and therefore it is a symmetrical alkene. But propene CH3 CH double bond CH2, on one side CH3 CH group, and on other side it is CH2 group. It is an unsymmetrical alkene. In such unsymmetrical alkene, but1 is an unsymmetrical alkene. In such alkene, when hydrogen halide is added, the negative part, the halide ion, goes to the carbon atom containing least number of hydrogen atom. This is because there is possibility of, in the case of ethene, that is, if the pi bond is shifted to any one of the carbon atom, you will get a ethyl carbocation. To that carbocation, the halogen atom is added, and you will get only one product. But if you take propene, if the pi bond is shifted to the first carbon atom, you will get, that is, CH3CH plus CH3, that is, it is a secondary carbonium ion. But if the pi bond is shifted to the second carbon atom, you will get CH3, CH2, CH2 plus. It is a primary carbonium ion. And a secondary carbonium ion is more stable than primary, and tertiary carbonium is more stable than secondary. The stability of carbonium ion is the order tertiary greater than secondary greater than primary. Can be explained by the hyperconjugation. Anyway, that is, and therefore, when an unsymmetrical alkene propene is added with HBr, the H plus will be added to the, that is, the first carbon atom, and Br minus to the second carbon atom. You will get 2-bromopropane or isopropyl bromide, and that is, the addition follows Markovnikov rule. But if the same HBr is used in presence of peroxide, peroxides are free radical generators, and in presence of peroxide, the addition follows, that is, free radical mechanism, and that is HBr homolytically cleaved to give hydrogen free radical and bromine free radical, and the carbon-carbon double bond is also homolytically cleaved to give a diradical, and to this radical, that is, the Br radical is added to the first carbon atom, and you will get, that is, you will get the 1-bromopropane. Instead of 2-bromopropane, you will get 1-bromopropane. And that is, the addition is against the Markovnikov rule, and that is known as the Karash effect or peroxide effect. Here it is asked is, that is, reaction of HBr with propene in presence of peroxide is an example of, it is free radical addition. In the absence of peroxide, it is electrophilic addition. That is, double bond, there is addition reaction, and that is, in the case of reaction mechanism, all the organic compound will undergo 4 types of reaction only. One is substitution, another is addition, and the third is, that is, elimination, and the fourth one is rearrangement. These are the only 4 type of reaction undergone by organic compounds. That is, organic compounds can undergo either substitution. An atom or group of atom is replaced by another atom or group of atom, and that is a substitution reaction. And if double bond or triple bond is there, it can undergo addition reaction. And if that is a molecule is water molecule or HCl molecule, etc., are removed from that is a compound, it is elimination reaction, as well as there is rearrangement. These are the only 4 types. And this 4 type of reaction itself, the mechanism can be vary. For example, a substitution. And if the substitution takes place through electrophilic mechanism, it is electrophilic substitution. If it is taking place through nucleophile, that is, it is nucleophilic substitution, and both are polar mechanism because there is charge separation arises. And if it is occurring through non-polar mechanism like free radical mechanism, it is free radical mediated substitution reaction. For example, methane, when treated with chlorine in presence of sunlight, chlorine molecule homolytically cleave to give 2 chlorine free radical, and this chlorine free radical will attack the methane, and that is a HCl is removed and a methyl free radical is formed, and this methyl free radical will combine with another chlorine free radical to give methyl chloride. It is an example for the free radical mediated substitution mechanism. But if you consider that is alkyl halide, methyl chloride, the carbon chlorine bond is polar because chlorine is more electronegative than carbon, and there is a partial negative charge on the chlorine atom and a partial positive charge on the carbon atom. That is, the molecule is having a polarity with positively charged carbon atom. And if there is a positively charged carbon atom, then there is nucleophile can attack on that. If you use aqueous alkali, OH minus, sodium hydroxide dissociate to give Na plus and OH minus. OH minus is a nucleophile. It will attack the positively charged carbon center and it will remove the halide ion. You will get alcohol. That is alkyl halide. When treated with aqueous alkali, you will get alcohol. Is an example for a nucleophilic substitution reaction. Similarly, there is electrophilic substitution reaction if the attacking group is electrophile, and that is in the case of that is substitution that is taking place by an electrophilic mechanism. That is, electron-rich center is there, and the electron-rich center will be attacked by a that is electrophile. Then it will be electrophilic substitution mechanism. And similarly, there is addition also. Free radical mediated addition takes place by, that is in the case of peroxide effect, that is anti-Marconic of addition. And if usually the addition takes place by, that is the substitution, that addition reaction takes place by, that is the mechanism is the new electrophilic addition mechanism. And that is in the case of alkenes when treated with, that is hydrogen halide, you will get alkyl halide. It is an example for a electrophilic addition mechanism because H plus will be the electrophile attacking. And there is peroxide effect is free radical mediated, and there are nucleophilic addition in aldehydes and ketones. Aldehyde and ketone CHO group, and C double bond O group is polar with carbon is having partial positive charge and oxygen is having partial negative charge. Therefore, that is C plus, that is it is electron deficient. A nucleophile can attack, and thereby it is known as nucleophilic addition. Grignard reagent RMGX. R minus will be the nucleophile. It will attack the positively charged carbon center, and you will get alcohol. And we will discuss it later. And that about the various type of electrophilic addition, nucleophilic addition, as well as non-polar mechanism free radical mediated addition. Here the peroxide effect is an example for a free radical mediated addition reaction. Answer is C. The alkene which gives the same product with HBr in the absence as well as the presence of peroxide. That is, a peroxide effect is only for, that is, unsymmetrical alkene. If the alkene is symmetrical, there is no peroxide effect. And therefore here what is asked is, which among the following is a symmetrical alkene? Propene is unsymmetrical alkene, butene is symmetrical alkene, and therefore butene is the answer. The least stable geometrical isomer among the following is, the stability of isomer depends upon various factors. One is a steric effect, and in the case of, that is choice B, that is about the carbon-carbon double bond, there is CS3 twice CS group on the same side of the carbon. It is a cis isomer. Usually the cis isomer is less stable than the trans isomer. Here it is the most, that is least stable. It is nothing but choice B because of the steric effect. Identify the major product in the following reaction, that is C6H5, CS2, CS double bond CS2 plus Br. Usually we will see that it can be forming, that is, it is the addition follows, that is electrophilic addition, and therefore we will expect that according to Markovnikov rule, it is bromine is added to the second carbon atom, but there is a difference, that is because of the benzene ring. Benzene is electron withdrawing ring, and therefore the first carbon atom, that is CS2 group attached to the benzene ring, will be added with bromine, and therefore it is 1 bromo, that is 1 bromo, that is 1 phenyl propane, 1 bromo, 1 phenyl propane, that is choice is C. 19th question, treatment of an alkene with hot acidified potassium permanganate gives trimethyl acetic acid and acetic acid. The alkene is, alkenes when treated with, that is alkaline or acidified KMnO4, it is a powerful oxidizing agent, and it oxidizes it to carboxylic acid. And here, depending upon the the position of the carbon-carbon double bond, we will get various type of carboxylic acid. For example, butene, when treated with acidified potassium permanganate, you will get 2 molecules of acetic acid because it is CS3, CH3, CS double bond, CS3, and on the double bond, CS3COH, CS3COH. But butene, you will get propanoic acid and methanoic acid. Likewise, depending upon the double bond position and the group on the either side of the carbon-carbon double bond, the product will be different. Here, what are the compounds? The first compound is nothing but, it is a bond line formula is given, and you can see what is the formula of it is nothing but CS3, CH, CS double bond, CS and CS3. That is 1, 2, 3, 4, 5. It is a derivative of pentene, and on the third carbon atom, fourth carbon atom, there is a methyl group, 4-methyl pentene, and therefore you will get acetic acid is one of the, CS3COH is one of the formula, but another formula will be, that is 2-methyl propanoic acid, CS3, CHCS3, COOH. That means it is 2-methyl propanoic acid. Therefore, what is asked is trimethyl acetic acid and acetic acid. For obtaining trimethyl acetic acid, there should be 2, 3 methyl group on that carbon atom, and therefore the choice may be, that is C choice or D choice. But in C choice, the other product is not acetic acid, it is, that is CS3, CO, CS3. It is nothing but acetone, and therefore it is not acetic acid, and therefore the answer is E. E choice, the trimethyl acetic acid and acetic acid are the product of, that is treating with hot acidified KMnO4. The choice is E. 1 mole of an alkene on ozonolysis give 2 moles of a ketone having a molecular mass of 58 U. The alkene is. Ozonolysis means alkenes when treated with ozone, O3. A molecule of ozone can be added to the carbon-carbon double bond. That is, an alkene will have a carbon-carbon double bond, And when an ozone is added to the carbon-carbon double bond, you will get the ozonide. And the ozonide is having a formula like this. This is the ozonide. And there is one molecule of ozone is added to the carbon-carbon double bond to give the corresponding ozonide, which on hydrolysis with zinc and water, you will get, depending the carbonyl group, CO group is there, depending upon the other group, it can be an aldehyde or ketone. For example, if it is ethene, CS2 double bond CS2, here both are HCOH, HCHO. HCHO means it is formaldehyde or methanol. HCHO, formaldehyde or methanol. But if it is butene, butene means CS3CHO, CS3CHO, two molecules of acetaldehyde or ethanol. If it is 2-methyl butene, then it is CS3CO, CS3 acetone and ethanol or acetaldehyde. And if it is 2,3-dimethyl butene, then you will get two molecules of acetone, and that is the product of ozonolysis. 1 mole of an alkene on ozonolysis give 2 moles of a ketone having the molecular mass of 58U. And that is ketone with molecular mass 58U is nothing but acetone, CS3CO, CS3, that is C2H6O. C2 means 24 and H6 means 6, 30, and therefore that is CS3CO, CS3. C3 means 36 plus 6 plus, that is the oxygen, it is 16. It is 58. The molecular mass of acetone is 58, and therefore what is asked is there is 1 mole of an alkene on ozonolysis give 2 moles of a ketone having molecular mass 58U. The alkene is 2,3-dimethyl butene. 2,3-dimethyl butene. The choice is C. Identify the starting compound X in the following sequence of reaction. X give with aqueous alkali give Y, and that is aqueous alkali, it is nucleophilic substitution reaction if X is a saturated compound, and this Y on treating with concentrated sulfuric acid and on heating gives Z, and Z is on treating with base reagent. Base reagent is called alkaline KMnO4. You will get a diol, that is propane 1,2-diol. That means an alkene on treating with base reagent will give a diol, and therefore Z is propene. Z is propene. Propene on treating with alkaline KMnO4, you will get propane 1,2-diol. And if propene is obtained from Y is an alcohol, and alcohol on treating with concentrated sulfuric acid gave this dehydrated to give the corresponding alkene. Therefore, Y can be propane 1-ol or it can be propane 2-ol. Propane 1-ol or propane 2-ol will on dehydration give propane, and therefore Y can be propane 1-ol or propane 2-ol. And that is an alcohol is obtained from X when treated with aqueous alkali. That means X is an alkyl halide, and therefore it can be 1-bromopropane. 1-bromopropane on treating with aqueous alkali gave propane 1-ol, which on treating with concentrated sulfuric acid gave propane. Propane on treating with base reagent gave propane 1,2-diol, and that is in the case of X, Y, Z, and therefore the answer is C, 1-bromopropane. Which among the following alkenes can exhibit geometrical isomerism? I have already mentioned that geometrical isomerism can be exhibited by compound containing, that is the formula CAB, double bond CAB, where A is not equal to B. 2-methyl butene. 2-methyl butene cannot exhibit geometrical isomerism because CAB is equal to A is equal to B, and therefore it cannot exhibit. That is, the structure of 2-methyl butene is this is CS3, CS3. This is 2. Therefore, A is equal to B. It cannot exhibit. That is geometrical isomerism. Chloroethene. In chloroethene, CH double bonds, CHCl double bond CS2. A is equal to B. It cannot exhibit geometrical isomerism. 2-chlorobutene. 2-chlorobutene can exhibit. 2-chloro-2-butene can exhibit geometrical isomerism because A is not equal to B. A is not equal to B. CAB double bond where A is not equal to B. 2,3-dimethyl-2-butene cannot exhibit because A is equal to B. 2-methyl-propene cannot exhibit because A is equal to B. Therefore, the answer is 2-chlorobutene that can exhibit geometrical isomerism or cis-trans isomerism. And last question is, when ethene is passed through bromine water containing sodium chloride, the product that is likely to be formed are, that is, ethene when treated with bromine water alone, you will get 1,2-dibromoethane. That is, the double bond is added with bromine and you will get 1,2-dibromoethane. But here it is carried out in presence of a water containing sodium chloride. Therefore, there is chloride ions are also there, and therefore it can also give, that is, in the case of, that is, 1,2-dichloroethane can be given as well as, and therefore the answer is, that is 1 and 2 only, 1,2-dichloroethane and 1,2-dichloroethane, as well as it can give 1-bromo-2-chloroethane. Therefore, answer is 1, 2, 3, and that choice is C. The choice is C, and that is the way in which the organic reactions are taking place. ഇന്നത്തെ ക്ലാസ്സില് എൻ്റെ ലാപ്ടോപ്പ് ഇല്ലാത്തതുകൊണ്ട് എനിക്കറിയില്ല എത്രത്തോളം എഫക്റ്റീവ് ആയി എന്നുള്ളത്. എന്തെങ്കിലും അറിയണമെന്നുണ്ടെങ്കിൽ ചോദിക്കുക, പറയാം. Any doubt?
No, sir. No, sir.
ഒന്നുമില്ല. Okay, thank you very much.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.